Hello and welcome to my talk on covariant Lyapunov vectors, linear modes for turbulent background flow. This was supposed to be a presentation held at the Mathematics of Planet Earth conference in Garden Grove, California this month, so June 2020. However, due to COVID-19, the event got cancelled and I gave this talk earlier this month at a Zoom conference. Now this is a re-recording of my talk, mainly for better quality and to fill in the things that I've missed. Before starting, let me first acknowledge the project TRR181 for supporting my research and for inviting me to the mini-symposium. So, without further ado, let us jump into the presentation. If you've never heard the term covariant Lyapunov vectors, do not worry. During the next few slides I will explain the concept and the intuition behind covariant Lyapunov vectors. First of all, covariant Lyapunov vectors are objects in dynamical system theory, and for me a dynamical system is best depicted as the vector field. Classically, we try to solve the underlying differential equation of this vector field, meaning if we have some initial condition or some starting point on this vector field, we try to find a path going through the starting point that is tangent to the errors. And if we, for all starting points, describe the path or the solutions simultaneously, we have the flow of this vector field. In particular, we are interested in qualitative features of this flow. Here you can see that on the horizontal line, all arrows are pointing towards the horizontal. So this means that the horizontal line is invariant under the flow. And in particular, the domain is separated into two flow invariant regions. If we start in the upper half and follow a trajectory, it will never path towards the lower half, and vice versa, the lower half is also flow invariant. In this talk, we are interested in another qualitative feature, namely the stability of solutions. This means if we have some reference trajectory with some initial position, we try to understand what happens if we have small perturbations to this initial position. Will the new resulting trajectory or solution have the same behavior approximately, or will it result in something completely different? Surely, the simplest kinds of reference trajectories you can imagine are stationary points. Those are points that do not change under the flow. In this vector field, you can see stationary points of different natures. For example, north of the center we have a stationary point that is attracting nearby solutions. South of the center we have the opposite, a stationary state that is repelling nearby solutions. And to the left and to the right of the center we have stationary points of hyperbolic nature, meaning that they have directions along which they attract solutions and directions along which they repel solutions. For now, let us focus on the stationary point right of the center. Here you can see the linearization around the steady state. The linearization gives us a good picture of what happens locally around the steady state, but not globally. However, when analyzing small perturbations to reference trajectories, the local picture around the steady state is often enough. It is quite well understood what happens to perturbations for linear systems. Essentially, the tangent dynamics or the linearized system is described in terms of eigenvectors and eigenvalues. The eigenvectors and the span of eigenvectors corresponding to one eigenvalue, so the eigenspaces, they form invariant directions under the linearized flow, and perturbations along those directions, they expand or contract exponentially fast with a rate given by the real part of the associated eigenvalue. The imaginary part then might lead to a rotation inside the associated eigenspace, but it is not important for the rate of contraction or expansion, which is described by the real part of the eigenvalue. Here for our example vector field we have two invariant directions. In orange, the unstable direction spanned by an eigenvector corresponding to an eigenvalue with positive real part, and a stable direction in blue corresponding to an eigenvector that has an eigenvalue with negative real part. So what happens if our reference trajectory is not a stationary state, but something else like a periodic orbit? For periodic orbits, we know from Floquet theory that we get a similar picture for the linearized model. So we can expect at each point along the reference trajectory a splitting of the tangent space into stable and unstable directions, plus the direction tangent to the reference trajectory, And perturbations along the stable direction, they decay exponentially fast. Perturbations along the unstable direction, they expand exponentially fast. However, this time the flow moves along the reference trajectory, so we have to define such a splitting along each point of the reference trajectory, and perturbations now also move in this blue stripe here, the blue bundle, or the orange bundle. So we don't have single spaces anymore, but rather invariant bundles for the linearized flow, along which perturbations decay or expand exponentially fast. Unfortunately, many problems produce more complex behavior rather than steady states or periodic orbits. And now the question is, for more general background trajectories, do we get a similar picture as above? So, can we expect invariant bundles under the linearized flow, along which perturbations decay or expand exponentially fast? This question was answered in 1968 by Lorenz' famous multiplicative ergodic theorem. In his theorem, he generalizes the classical stability theory to more general background trajectories. The eigenvalues of Floquet exponents for steady states and periodic orbits now become Lyapunov exponents. The directions corresponding to those exponents, the eigenvectors, now are covariant Lyapunov vectors, and the spaces spanned by those vectors, the eigenspaces, now are oscillated spaces. So we get a complete picture generalizing the classical stability theory to more general trajectories. However, note that the eigenvalues have an imaginary part, so there's also the rotation parameter encoded for steady states and periodic orbits. We don't have that for general trajectories. Lyapunov exponents are real, so they are missing the imaginary part and can only encode contraction or expansion. Since the original version of the multiplicative ergodic theorem by Lorenz, there were several new versions. I mostly worked with versions in Ludwig Arnold's book on random dynamical systems. That is for finite dimensional systems, and for infinite dimensional systems I consulted the paper A Semi-Invertible Operator of the Lorenz Theorem by Cecilia Gonzalez-Stockman and Anthony Quaz. Really, the first application that comes to my mind is the sensitivity analysis through covariant Lyapunov vectors, and there I want to mention the work of my former colleague Sebastian Schubert and his supervisor Valerian Lucarini, who applied the concept of covariant Lyapunov vectors to an atmosphere model PUMA and an ocean atmosphere model MAOAM. And then later Melinda Galfi, another colleague of mine, continued the work of Sebastian Schubert in addition to her own work. Concerning the sensitivity analysis and statistics part, I'd also like to mention the work on applying CLVs to find improved shattering trajectories by Angxue Ni and Kiki Wong, and also Nisha Chandramurthy, who I met last year during the SIAM conference on applied dynamical systems in Snowbird. Since covariant Lyapunov vectors form a basis of the tension space, we can use them for mode reduction or decoupling of the tension space. And there I want to mention the paper below by Takeuchi, in which he advertises the use of covariant Lyapunov vectors and the decoupling for dissipative systems. And let me also mention the work by my colleague Melinda Galfi, who uses the decoupling through covariant Lyapunov vectors in the context of ocean-atmosphere models, and in particular for multiscale models, she tries to understand how the scales relate to the different covariant Lyapunov vectors. Last but not least, let me mention that you can use covariant Lyapunov vectors to find coherent structures. So coherent structures are slow-mixing sets, and by this I mean time-dependent subsets of the domain that change little over time under the flow. In order to find these coherent structures using CLVs, we need a functional analytic setup. And in this setup we usually evolve densities or observables using a transfer operator, sometimes called Perrin-Frobenius operator, or its dual, the Koopman operator. If we look at this operator for discrete time steps, we get a sequence of operators on Banach or Hilbert spaces for which we can apply the infinite dimensional version of the multiplicative ergodic theorem, which I mentioned before. The theorem then gives us covariant Lyapunov vectors, which somehow encode the coherent structures. You can read more about this in the works of Cecilia Gonzalez-Stockman and Chantal Blachou, and also some works of Gary Froyland. Now that we've seen several applications of covariant Lyapunov vectors, we asked ourselves, how do we compute covariant Lyapunov vectors? There are several algorithms to compute covariant Lyapunov vectors. Some of them have a more static approach using a singular value decomposition of the linear propagator, and some have a more dynamical approach using forward and backward propagation along the background trajectory using the linear propagator. Most algorithms rely on one of the two approaches or combine them in order to compute CLVs. They also differ in their implementation, especially the kind of matrix decomposition that is used. A nice overview on CLV algorithms can be found in the paper mentioned below by Gary Freund and his colleagues. In this talk, however, we focus only on one CLV algorithm, namely the Ginelli algorithm. This is the most used and most famous CLV algorithm and was published in 2007 by Ginelli and his colleagues. Ginelli's algorithm is a dynamical algorithm that computes CLVs and also the Lyapunov exponents as a byproduct. Aside from the multiplicative ergodic theorem, we don't really need any additional assumptions. During the next slides, I would like to show you an overview of Ginelli's algorithm before we look at a numerical example and my research concerning the convergence analysis of Ginelli's algorithm. Given some background trajectory in the linear propagator, we would like to compute CLVs, let's say at the point t2. And for this, we need data along the path of the trajectory until some point t1, and the future part of the trajectory until some point t3. Now, Ginelli's algorithm basically consists of two phases. First, the forward propagation, and second, the backward propagation. In the forward propagation, we have one set of initial vectors, which we first propagate from the past to the present, so from t1 to t2, and then further from the present to the future, from t2 to t3. And in the backward propagation, we have another set of initial vectors, which kind of depend on the first phase, and those we propagate backwards from t3 to t2. Then there are also some numerical subtleties to the algorithm, like using an osmolization procedure during each time step to ensure numerical stability of the algorithm. You can read more on those in the original version of this algorithm in Ginelli's paper. However, since the numerical details do not really change the analytical result of the algorithm, let us keep it simple for now and only look at the analytical part. Let me briefly give you an idea of what is behind the first and the second phase of Ginelli's algorithm. Looking at forward propagation, first imagine one vector in tangent space that can evolve freely over time. So we propagate this vector forward and see that it will align with the fastest expanding direction, that is the first CLV. What happens if we have a second vector? Well, nothing special will happen. This vector, like the first vector, will align with the fastest expanding direction, so the first CLV. However, if we look at the span of the first two vectors, this will give us a two-dimensional subspace, which will align with the fastest expanding two-dimensional subspace, that is the span of the first two CLVs. Similarly, we can look at more initial vectors, and if we propagate them forward, we get a similar result. So let's say for k vectors, the k-dimensional subspace spanned by those vectors will align with the fastest expanding k-dimensional subspace, that is the span of the first k CLVs. At least analytically, that's how we compute spans of the first CLVs. And let me comment on numerical stability here. So numerically, we would run into a problem if we only propagate forward, because as I told you, almost every initial vector will collapse into the first CLV. In particular, looking at two vectors, we would lose track of the subspace spanned by those two vectors after some point. So in order to prevent this problem, the algorithm uses a QR decomposition, which keeps the first vector and the second vector at a certain angle. This allows the first vector still to evolve freely, and the second vector to evolve freely in the orthogonal complement of the first one. But this is enough for the two-dimensional subspace spanned by them to evolve freely. So, now we have computed the spans of the first CLVs at our present state, so state t2. But what we really want are only the single CLVs. So CLV1, CLV2 for the two-dimensional case, CLV3 for the three-dimensional case, and so on. Somehow we need to extract the single CLVs, the last components of those sums. How do we do this? To extract the last component, we need to look at the system with reverse time. So you might notice that the last component is always the fastest expanding direction in backward time. So in particular, using the same method but for backward time, we would be able to extract the last component of those spans. So what we really need is a good enough approximation of those spans for a long enough time span. And for this, we use the next step. In step 1.3, we just continue what we did in the previous step, step 1.2, and propagate the spans of those vectors forward. So we have a good enough approximation of CLV1, CLV1 plus 2, CLV1 plus 2 plus 3, and so on a long enough time frame in the future part of the trajectory. Arriving at T3, a point far enough in the future, we then initiate a new set of initial vectors, here in blue, subject to the spans of the forward propagated vectors, and essentially do the same we did in step 1.2. So we propagate them backward and rescale them. From this we hope to get an approximation of the CLVs. Aside from the numerical subtleties, this really is the analytical kernel of Giannelli's algorithm. Let me summarize again. So Giannelli's algorithm has two phases: the forward phase, in which we propagate the first set of initial vectors from the past until the future. Then, using the spans or the products of the forward propagation, we initiate a new set of initial vectors in those spans from the forward propagation and propagate them backward from T3 to T2 to get an approximation of CLVs. So now that we know what CLVs are, what application they have, and how we compute them, let me tell you a bit about my research. During my time as a PhD student at the University of Hamburg, I was mostly concerned with the convergence analysis of CLV algorithms. For this I focused on Giannelli's algorithm, but many of my results also are valid for other CLV algorithms. The main question I pursued were, does Giannelli's algorithm converge? If so, how fast is it? And what happens in different settings? And by this I mean what happens for discrete time systems, for continuous time systems, what happens in finite dimensional systems or in infinite dimensional systems. The main results of my work, which I want to present you today, are two convergent theorems in finite dimension, one for discrete, one for continuous time stepping of the algorithm, and another convergent theory in infinite dimensions for discrete time stepping. But before we jump into the theorems, let me give you a numerical example that displays the convergence behavior of Giannelli's algorithm. As a test case, I chose the Lorenz 63 model with its classical parameters, which gives us a chaotic attractor. The attractor emits an SRB measure and has ergodicity, so the multiplicative ergodic theorem applies and gives us the existence and uniqueness of covariant Lyapunov vectors and Lyapunov exponents almost everywhere on the attractor. And in particular, the ergodicity applies that the Lyapunov exponents are constant almost everywhere on the attractor. So it really should not matter which kind of trajectory on the attractor we use to compute the Lyapunov exponents. In this framework, I and others before me have computed Lyapunov exponents and CLVs of the Lorenz attractor. But let me also mention that the support of the SRB measure only has Lebesgue measure 0. So in particular, the multiplicative ergodic theorem, which gives us existence and uniqueness of CLVs, only holds on a set of Lebesgue measure 0. So in order to verify the numerical results, more work on the theoretical side would be needed. Even without full theoretical justification yet, let me show you what happens with Giannelli's algorithm in this scenario, in particular looking at convergence properties of the algorithm. For this test case, I combined the nonlinear version of the Lorenz system with its linearized version and integrated the system using a fourth-order Runge-Kutta method. Here you can see the trajectory corresponding to the nonlinear part of the solution. I integrated the system for 50 units of time in blue, and then for another 50 units of time in orange. And the state in between, the black dot here, I called the current state. This is what I called T2 on the previous slide. And here T1 would be at the beginning of the blue part and T3 at the end of the orange part. The linear part of the solution to the combined system gives me the linear propagator along this trajectory. To analyze convergence of Genet's algorithm, I computed the CLVs with varying amounts of past and future data and compared it to the CLVs I obtained with 50 units of time for past data and 50 units of time for future data. Here I plotted the logarithm of the error and compared it to the distance between the associated Lyapunov exponent, that is the first Lyapunov exponent, and its neighboring exponents. So in this case only the distance between the first and the second Lyapunov exponent. We see quite nicely that with increasing amounts of data, which linearly relates to the computational time, the logarithm of the error decays with a rate given by the distance between the first Lyapunov exponent and the second Lyapunov exponent. So the error decays exponentially fast with a rate given by the distance between the first and second Lyapunov exponent. That is until system accuracy is reached. We can see a similar behavior for the second CLV, where the error again decays exponentially fast with a rate given by the spectral gap between the second Lyapunov exponent and its neighbors. And the slope is the same as for the first CLV because the distance between the first and second Lyapunov exponent is smaller than the one between the second and third Lyapunov exponent. Whereas for the third CLV, we have a much faster convergence, which is due to the large gap between the second and the third Lyapunov exponent. In a way, we can identify the inverse of the Lyapunov exponent as a timescale of the corresponding CLV. And here in this example, the timescale of the third CLV is much more different than the other two timescales, thus the algorithm can distinguish the third CLV from the other two much faster. From this example, we have seen that we can expect Genet's algorithm to converge exponentially fast, where the convergence to each CLV depends on the corresponding Lyapunov exponent and its neighboring exponents. This is not just a feature of the Lorenz system, but rather I could show analytically that given the assumptions of the multiplicative ergodic theorem, we can expect such a convergence. I could show that Genet's algorithm converges for almost every initial condition, and if you go back, by this I mean the two sets of initial vectors in Genet's algorithm, one I had in red and the other I had in blue. And I could also show that the convergence is exponentially fast with the rate given by the spectral gap between associated Lyapunov exponents. Looking at this formula, if you for 1 second forget the lim sup in the beginning, multiply it by t, take the exponential function, then you see that the distance of the approximation is less or equal e to the power of minus t times the distance of the associated Lyapunov exponent to its neighbors. This form of the formula is for non-degenerate systems. I also treated the case of degenerate systems, meaning that the Lyapunov exponents might have higher multiplicities, leading to higher dimensional oscillated spaces. For example, if the oscillated spaces, which were the equivalent to eigenspaces for steady states, if they have some internal dynamics like rotations. And then I also looked at what happens if we have different amounts of data for the past and future of the trajectory. It turns out that you really need past and future data, and you need to increase them both to get an succeedingly better approximation of the CLVs. Then I looked at what happens if we go from discrete time to continuous time systems, and first of all, numerically you would always go back to the discrete time version, because the time stepping that is necessary due to the computer is discrete, so you have a discrete time version and you have convergence almost everywhere. However, if analytically you have a continuous time stepping in the algorithm, then the convergence will not hold almost everywhere. We have convergence, but in a weaker sense. So the theorem which I've proven says that Genet's algorithm converges in measure instead of almost everywhere, but also with the same convergence speed. For those two theorems, I used the multiplicative ergodic theorems found in Arnold's book on random dynamical systems. And now for my next theorem, which is a similar version but for infinite dimensions, I used the multiplicative ergodic theorem by Cecilia Gonzalez-Tockmann and Anthony Quaz. Their multiplicative ergodic theorem is valid for separable Banach spaces and for example used in the context of coherent structures. For my new proof, however, I restricted myself to separable Hilbert spaces, on the one hand because of proof details, and on the other hand because Genet's algorithm, or at least the numerical implementation, uses the Gram-Schmidt procedure, which makes sense in Hilbert spaces. In this setting, similar to the finite dimensional case, I could show that Giannelli's algorithm converges for almost every initial condition, and moreover that the convergence is exponentially fast with the same rate that we had before. While at first glance the theorem sounds rather similar to the one for finite dimensions, it is different in its details, and also the proof required some new techniques. First of all, in infinite dimensions, the Lyapunov spectrum, which is the collection of all Lyapunov exponents, doesn't have to be discrete anymore. It could, for example, have some continuous parts. And this is where the quasi-compactness assumption of the multiplicative ergodic theorem comes into play. The assumption ensures that the highest Lyapunov exponents are discrete from the rest of the spectrum, and that covariant Lyapunov vectors, or more general oscillated spaces, exist for those exceptional Lyapunov exponents. Another difficulty arising in the analysis of Giannelli's algorithm in this new setting, using the multiplicative ergodic theorem by Cecilia Gonzalez-Togma and Anthony Quaz, is the semi-invertibility. The semi-invertibility means that the linear propagator along the reference trajectory must not be invertible anymore. And especially for the second phase of Giannelli's algorithm, where we need to do backward propagation, this might be a problem. In the end, the backward propagation is restricted to subspaces which we get from the forward propagation. And if the subspaces from the forward propagation are good enough approximations to the first oscillated spaces, then it is far enough away from the kernel of the operators, and thus we can ensure that the operator for the backward phase restricted to the subspaces is invertible. The last point I would like to mention concerning the transition from finite to infinite dimensions was already in the statement of the theorem. There I said that Giannelli's algorithm converges for almost every initial condition. You might ask yourself, what does it mean for almost every? Well, in the finite dimensional case, this is clear because there we have the Lebesgue measure, and there the statement of the theorem says that it converges for almost every initial condition with respect to the Lebesgue measure. In infinite dimensions, however, we don't have an equivalent of the Lebesgue measure. There I use the notion of prevalent, which generalizes the concept of Lebesgue almost everywhere to infinite dimensions. It doesn't give us a new Lebesgue measure, it only generalizes the notion of Lebesgue almost everywhere. Having analyzed convergence of Giannelli's algorithm in finite and in infinite dimensions, I would also like to know what happens in between. So what happens with CLVs, Lyapunov exponents, and also Giannelli's algorithm in the transition from finite to infinite dimensions? I think this would be a nice topic to study, and also it would have relevance to applications. To conclude, I showed you that we can generalize the classical stability theory to more general background trajectories using the multiplicative ergodic theorem. The multiplicative ergodic theorem gives us the existence and uniqueness of covariant Lyapunov vectors, so the directions and associated growth rates given by the Lyapunov exponents. Then I showed and explained to you Giannelli's algorithm as a way to compute CLVs. After looking at the Lorenz structure as a numerical example to motivate the convergence results, I showed you two convergence theorems in finite dimensions, one for discrete time, which said that Giannelli's algorithm converges almost everywhere and is exponentially fast, and one for continuous time stepping of the algorithm, which said that Giannelli's algorithm converges in measure and is also exponentially fast. Then we had another convergence theorem, but this time in infinite dimensions for discrete time in a semi-invertible setting, and still we got the same result, so we have convergence for almost every initial condition and exponentially fast. If you'd like to find out more, please have a look at the various papers that I mentioned during our presentation. Thank you for listening, and goodbye.